Hello, my name is Peter, and today this is my presentation on the second lab of Physics 1, talking about projectile motion. And so what is the main purpose of this lab? We are investigating into the essential concepts behind the idea of projectile motion, observing an object over a brief period of time that's thrown in a parabolic-like path, and comparing these observations to two computational models, which will make one taking into consideration air drag and one without taking into consideration air drag. And then ultimately we're looking for differences between our actual observations and our computational models in order to extract some type of conclusion, helping us better understand the idea of projectile motion. So the fundamental physical principles behind this lab is the idea of how when an object is thrown in motion, so it follows a projectile-like path, the object is at least taking into I should say the object is at least experiencing the force of gravity, which is often what we only take into consideration in Physics 1. However, in real life, there is in fact another force due to air drag, which we don't really touch on in Physics 1, and so that's what we're investigating in this lab. So the models we use are the video imported into Tracker and the computational models which we create with GlowScript. And in the end, the computational model, which took into account the effect of air drag, more accurately predicts the final Y position, the final height, as the object we've seen observed in the video. However, this affects the earlier Y positions in the predictions, and we'll see this explained later on in more detail. So here are the main physics ideas. Basically, these two are essential to our coding. Velocity update formula derives from the momentum principle, and then put that into the position update formula to update position. And then we have the two essential forces, force of gravity, opposite of the positive Y position, so towards the center of Earth, the mass of the object times the gravity or gravitational constant near the surface of the Earth, all in the Y component of the vector. And the drag force, which we haven't really talked about too much, but for the purpose of this course, it's always against the direction of motion, and then you have to take into consideration the proportionality constant, which is basically based on the type of object itself, and then the environment in which it is moving through. So there's a lot of different factors which affect B, and then this is just the vector velocity here. So here's the actual lab. It's a little different because we're not actually starting at the origin, which is down here, as you can see with the axis. But I'm starting basically, you can't see the hand here because it's the later frame, but basically someone's throwing this, and their throwing motion has a force which is not taken into consideration in the code over here. So I made the starting point of the object, the point at which it has just left the hand of the thrower. So that's why this looks a little different than just a simple parabola. And then the initial conditions here, we get the vector velocity by doing a simple displacement over time from here to what I consider the starting point for the purpose of this lab. And then you can see we've coded for the force of gravity and the force of air drag, which we did not initially, but made sure to update. And in this scenario, we have the system as the crumpled up piece of paper and code the ball, and then the surroundings are everything else. So the conclusion is that the model which takes into account air drag in the end more accurately predicted the final Y position, as can see here. Here's the green one, the model with air drag, very close to the experimental Y position. However, this skews the earlier predictions to be not as accurate as the model which actually does not take into account air drag. And so basically this lets us ascertain that air drag is more complex than what we have coded for. And yeah, basically we would need to delve into the actual idea of air drag some more before we can actually make some applications and predictions. This is essentially what I've garnered from this. And then the what if question, so what if the object was initially thrown straight up with the same initial speed as in our experiment? So basically the speed would be built up all into the Y component of velocity, meaning on its descent there would be greater air drag and it would take longer to reach the ground. And so what does this mean? In order to investigate into the idea of terminal velocity, we would need to create a model which has a descent completely in the negative Y direction. And that's it. Thank you.